Okay, so hi everyone. Um, so obviously, the last couple of days has been exciting with the election and so on, but it's time to think about some quantum error correction again. Um, so I also want to emphasize project proposals are due today. I expect that the correlation between people attending this lecture in person and people who've submitted project proposals already is pretty high. But if you haven't, please do. If there's any problems showing up, you're struggling to find team members or anything going wrong, then please tell me today. Okay, so that's the administrative stuff. So last time we introduced the idea of quantum error correction, and in particular, we introduced probably the simplest to understand quantum error correcting code, which is the short code. It's a code that encodes a single logical qubit, single qubits worth of information into 9 physical qubits that are, the actual things you store it as that may have errors, and protects it against any error happening, any infinitely many possible errors happening on one of those 9 qubits, as long as there's only an error on one. Okay, so today it's just going to be more quantum error correction. In particular, we're going to introduce a sort of very general framework for creating quantum error correcting codes, which are called stabilizer codes. Okay, so at the very end of last time, I claimed that there is a general condition necessary and sufficient condition for quantum error correction to be possible. And it's defined as follows. We first need to define some set of errors. Okay, just a set E1, E2, so on, which we'll take to be different. These are different unitary operators that we describe some error process happening to that qubit, and they're the errors that we want to be able to correct. We'll call them correctable errors. Okay, so for the short code, for example, this set would be 1 qubit Pauli matrices. Pauli matrices that act just on a single qubit and do nothing to the rest of the qubits. Okay. It's also worth noting that we can also correct superpositions of these errors. Okay, so even though that's just a finite set of errors and there's infinitely many, then any operator acting on 1 qubit can be written as a sum of Pauli operators and the identity. And so that lets you regard any arbitrary operator getting applied to that 1 qubit as creating a state that's a superposition of nothing having happened, an X gate having been applied, a Y gate having been applied, and a Z gate having been applied. And so then, we can our error correcting process automatically both determines which EI it was and recovers from that EI. Okay. And then, so we also need to define a code subspace. Okay, so this is the set of the subspace of states that logical qubit states get encoded as within the larger space of physical states. So this is the subspace of logical states. And we're going to assume that that has some orthonormal basis given by the states I tilde. Okay, it's an orthonormal basis just for this subspace, not for the entire physical Hilbert space of 9 qubits or whatever. Okay, and then we're now ready to define the condition for quantum error correction, which is that for any j tilde, any error EB dagger, any other error EA, and any initial state I tilde, that inner product has to be equal to CAB delta IJ for some matrix CAB. Okay, that is independent of I and J. Okay, so the simplest case, recall, is that when CAB is just delta AB. Okay, so that meant that, you know, all the subspaces created by acting with error EA on the code subspace were all orthogonal to one another. They all had zero inner products with one another. So you can just do some measurement that determines which of those subspaces you're in and therefore determines which EA happened. Okay, and then you can just apply an EA dagger to undo that process and recover the original state. Okay, however, you know, that's just a specific class of quantum error correcting codes called non-degenerate codes. Many codes, such as the Shor code, don't work like that. So the general condition is this one, and last time we did not attempt in any way to prove this condition. So that's what we're going to start by doing today. Okay.
Just
any questions on that?
Quick question.
Yep.
The e's, you said there's a finite number of e's, but then because you can consider superpositions as infinitely.
Yep.
Did I get that correct?
Yep, that's correct. Exactly. So e's for the Shor code would just be, you know, the identity, x acting on first qubit, y acting on first qubit, z acting on first qubit, x on second, so on. So there'd be what, 1 plus 3 times 9, so 28 of them. But really, we can correct anything that happens at all to a single qubit. Cool. Okay. So we need to prove that this condition is both necessary to be able to correct errors and is sufficient to be able to correct errors. So let's start by proving that it's a necessary condition. Okay. So what we're going to do is going to consider the quantum channel that takes rho to sum over A, EA rho, EA dagger. Okay, and then we normalize it by dividing through by the number of different possible errors that can happen. Okay, so what this channel does is it applies a random error from the set. Okay, so we can also write this in Stein-Spring picture, okay, where there's some environment E. And in the Stein-Spring picture, takes your sort of logical state, I tilde, tensored with the environment, always starts in state 0 for simplicity, and it goes to 1 over square root, it's the number of errors, sum over A, EA acting on I tilde, tensor the environment just being in state A, where A is some orthonormal basis. Okay. Okay. So we assume that's happened. We assume some randomly chosen error has been applied to our state, I tilde. And then we want to recover I tilde, okay, without knowing what error got applied. In other words, without having access to this environment system E, okay? So how do we recover I tilde? Well, how did we do it last lecture? Well, we first did a measurement and then conditioned on that measurement outcome, we did a unitary. So often that's in practice what you do in quantum error correction. But really, like, if you're not conditioning on, you're not relying on getting a certain measurement outcome, then measurement can just be described as a quantum channel, right? That's sort of the lesson we learned from a few lectures ago. And a unitary is also a quantum channel, okay? So we can combine those two things together and just say we want to use some second quantum channel that we'll call the recovery channel. And we want our output of that channel to always just have the state of the system be in the state I tilde again, okay? So the error has gone away. So this channel can describe measurement process, unitary gates being applied, etc. Okay. Everyone clear on anyone have any questions about like why that's the the most general thing we can do to try to recover the state? Okay, it's the most general evolution we can do by doing measurements, interacting with an environment, like whatever we want. Okay, so this channel should have some Krauss representation, which is going to be a set of operators R mu dagger, R mu equals the identity. Okay, and that will take this state, our initial state with the error applied, to the following state, 1 over square root of E, sum over both A and mu now. We have an R mu being applied after the EA, I tilde. We have A from the environment from our error process, and then this recovery channel has its own environment, which we'll call E prime, and that's going to be state mu, okay, where mu is again just an orthonormal basis for the environment. Okay, and what we want is for this whole complicated state that's had this whole process applied to it to just be the state I tilde tensor some stuff in the two environments, some fixed state in the two environments. Okay, so in particular, this state needs to be independent of I tilde. Otherwise, if you had superpositions of I tilde, then the state would get entangled with the environment and it would decohere. Okay, it would have effectively gone measured. Okay, but if we have just the end result is the system is in state I tilde and then E and E prime are together in some state, whatever that might be, then we've got, nothing has happened to the state. There's just been some evolution to the environment and we've corrected the error. Okay, any questions about that? Okay, so this condition is true if and only if R mu EA acting on I tilde is just equal to, it has to be proportional to I tilde, right? Because we need to always end up with the state being I tilde, the system being I tilde. So something proportional to I tilde, but also we need these lambda coefficients to be independent of I. Okay, if they're not independent of I, then the state of the stuff is going to depend on what I was, because the state of the stuff is going to be, this stuff is going to be equal to sum over mu A, lambda mu A, A mu. Okay, so we need those lambdas to be independent of I. Okay, so let's say that's true. Then the following is also true. We do EB dagger, R mu dagger. Okay, that's just the dagger of R mu EB. Okay, and then we apply that to R mu EA I tilde. Well, the R mu EA just takes I tilde to lambda mu A I tilde. And then the dagger of R mu EB acting on I tilde is just going to take it to lambda mu B star of I tilde. Okay, so it's again, these two things we've applied, still just going to leave our state proportional to I tilde. Finally, can use linearity to do a sum over mu here, sum over mu the other side. Okay, we still just have something proportional to I tilde. But we know we can take this sum over mu. Yeah, sum over mu, R mu dagger, R mu is just the identity. So this is equal to EB dagger, EA, I tilde. Okay, so we have the EB dagger, EA, I tilde has to be equal to some constant, some over mu of lambda star mu B, lambda mu A, but that in turn is just some matrix, CAB. Okay, so this thing equals CAB I tilde, which immediately implies J tilde, EB dagger, EA, I tilde equals CAB delta IJ. Okay, so we've shown that the assumption that we can correct a randomly chosen error from if a randomly chosen error is applied to the logical state, then we can use some other channel to get back our logical state necessarily implies that the errors must satisfy this property here. Okay, so we proved it's a necessary condition. Any questions about how that proof worked? Okay. Let's do sufficient condition as well. Don't worry, this proof is fairly technical. So if you're struggling to follow the details but still don't want to ask questions, then you can go over it afterwards or just accept the condition and just believe it. But I did want to show explicitly to you guys why it's true. Okay, so we're going to prove it's a sufficient condition by constructing an explicit recovery channel with Krauss operators on mu. Okay, that will work whenever we're going to rely on this condition being true, but whenever this condition holds, then the construction will work and it will recover the state. Okay, and the way we're going to do that is we're going to define some new matrices, mu, going to be the sum over A of E mu A times EA, where E mu A is just the coefficients of the muth eigenstate of the matrix CAB. Okay. So what does this do? Well, then it's easy to see that if we take J tilde, mu dagger, mu I tilde, then we get a sum over A and B of E nu B CBA EA mu times delta ij. Okay, but this is of course, because CBA is an eigenvalue, sorry, EA mu is an eigenstate of CBA, and the E mu's and E nu's form an orthonormal basis, then this is just equal to delta mu nu, right, times C mu, well, that's the eigenvalue of CBA for that particular eigenstate, times delta ij. Okay, so by working with this set of operators M mu rather than the set of operators EA, we've diagonalized the matrix CBA. Totally standard thing to do anytime you have a matrix, right? Okay, so now we've got our M mu's. We're going to define just explicitly the recovery channel by R mu equals 1 over the square root of C mu sum over I M nu dagger. Sorry, M mu dagger. Okay. So yeah, this is just a set of operators R mu. That it's reasonably easy to see, like if it was a non-degenerate code and this matrix CBA was already just delta mu nu, then these operators M mu would just be the EAs. We wouldn't need to like change the basis, and you can check that this recovery channel would then just be like R mu is like measuring the error and then measuring that the error is A and then applying EA dagger. Okay, so that's the thing we said before would work for non-degenerate codes, but this is a more general definition that works for any code, and it's often called so-called PETS map, PETS recovery channel. Okay, there's other channels that will work as well, but this is a particularly simple one. Okay, so now we're going to suppose we have some error. Okay, we're not going to assume it's just a single error EA. We're going to allow it to be a superposition of different errors. We're going to allow it to decohere in the environment. So the most general thing that's allowed to happen is that we have the state I, the environment starting in the 0 state, goes to sort of a sum over errors of EA acting on I tilde, tensor, some state psi A of the environment that is in general not normalized. Okay, so we're just expanding this as a superposition of different errors EA and then absorbing the amplitudes into this non-normalized state psi A. However, by a change of basis, it must also be possible to write that state as the sum over mu, M mu acting on I tilde times some state psi mu of the environment. Okay, for a new set of non-normalized states, psi mu. Okay, now we're going to apply the recovery channel. What does that give us? Well, we started with a sum over mu, M mu. We now have a sum over nu, R nu, M mu, I tilde, state psi mu, the environment, times some orthonormal basis for this extra environment, E prime, state mu. Okay. What is this equal to? 1 over square root C nu, sum over nu mu I tilde, m nu dagger, m mu, I tilde, psi mu, nu. Okay, this is just writing out this explicit definition of R nu that we wrote up here. And in turn, because we have, let's make this sum over J to distinguish it from I. Because we had this relationship that J tilde mu dagger mu I is just C mu times delta mu nu times delta ij. This sum simplifies dramatically, and we just get that the state ends up being the square root of C mu times I tilde times psi mu E times nu E prime. Okay. Which is, of course, I tilde tensor stuff, as we desired. Okay. So we have recovered I tilde. You might, if you've been paying enough attention, worry a lot at this point because we define this set of Krauss operators R mu, but there's a very important property of Krauss operators which they have to add up to the identity. We need the sum of mu R mu dagger R mu to equal the identity, or this isn't an allowed channel. It's not something we can physically do. Okay, so fortunately, we can deal with this. So let's just look at what sum over R mu dagger R mu actually is. Well, we have a 1 over square root C mu from each of them, each of the R mu and the R mu dagger. Sum over mu, 1 over C mu. Have an I tilde, M mu dagger, and then another sum over J tilde that just diagonalizes, and we have an M mu there. Sorry, yep, that's right. Turns out, you can check, I'm not gonna justify it properly, but this just acts as a projector onto the subspace spanned by errors EA acting on I tilde. Okay, acting on any state I tilde. So it's the set, it's a projector onto the subspace of states that can be created by acting with some error EA on some state in the code subspace. What does that mean? Well, it's not the identity, so we're not quite done, but we can turn it into a actual quantum channel by adding just one extra Krauss operator. You can call maybe R0, just going to be a projector onto the orthogonal complement of that subspace. Okay, that makes it add up to the identity. So we're summing to the projector and its orthogonal complement. And you can check that R0 acting on this state mu nu I tilde psi mu is just going to give 0, right? Because by definition, R0 is orthogonal to all states that can be reached by errors acting on states in the code space. Okay, so we have success, we have constructed a channel, we've proved this is a sufficient condition in addition to being a necessary one. Okay, so that was fairly technical. Anyone have any questions on it?
I did have a quick question.
Yep.
At some point, you made it a point to note that the state we get after applying our error is non-normalized, or it wasn't normalized.
Yeah, that
Was there a reason we noted that?
Not terribly important, just that it isn't. And in fact, if it was normalized, given these EAs with unitaries, then the whole state would become non-normalized. Let me actually change from talking about it being not normalized to just gonna add some amplitude CA out the front here. And we're gonna add some amplitude C mu out the front here, and then it can be normalized. Okay.
And then when you were applying this recovery channel, it seems like we took the sum over nu as well, but then the final state is still dependent on, like the ancilla for the recovery map is also still seems to be dependent now. Okay.
Yeah, that sum got dropped. This stuff, yeah,
it has the sums in it.
Is equal to yeah, sum over mu. Okay, let's put, now I need to put my C mu's in here as well. C mu.
Sorry.
Now let's call these A to distinguish them from the other C mu. Okay, we have an A mu here. Have an A mu here. Stuff, sum over mu nu, A mu, square root big C mu, psi mu. Okay, some complicated, messy state, but you know, we've extracted all the complicated and messiness out of the system and into the environment. Okay. Any other questions about how that proof works?
So in like the whole argument, you seem to be using the I tildes, and I'm assuming they're like one of the
yeah, I'm just working in a basis of the code subspace just for simplicity. Doesn't matter what basis I use, but the point is that these I tildes are they're an orthonormal basis of logical states. Okay, so they're not a basis for the whole Hilbert space. You know, for the short code, you just have 0 tilde and 1 tilde, which is just the way you encode your 0 state and your 1 state into these 9 qubits. Okay, but there's 2 to the 9 states in total in the full 9 qubit Hilbert space, and most of them are not logical states I tilde. Is that clear?
Yeah, okay.
Okay, so let me make a few comments before we move on. Okay, so the first comment is that sort of in the last lecture, it seemed like doing a measurement to learn what error happened was crucial, right? And like that's how we thought about doing things. We do a measurement. Once we've learned the measurement, we do something else. But really, doing a measurement and then doing something else, if you don't care about the results of the measurement, or you just do something different things conditioned on the results of the measurement, but it like works regardless of the results of the measurement, then that's just a quantum channel. And a quantum channel you don't need to think about a measurement happening in that. You can think of a quantum channel as just a unitary interacting with some environment and then throwing stuff away. Okay, so doing a measurement is not crucial to quantum error correction. What is crucial though is that this recovery channel can't just be a unitary, right? If we have some unitary channel, if our initial process has entangled our system with the environment, right? We have something like this, superposition over A of EA acting on I tilde, tensored with the environment being in state A. If I then just apply some unitary to the system, that can't change the fact that my system is entangled with the environment. And so I can't get the system back to definitely being in the state I tilde. Okay. So it is crucial to have some degrees of freedom. They're often called ancilla qubits. Right, they're the things I called E prime in the calculations above, that you throw away during the quantum error correction. Okay, so these can be thought of as like the extra qubits that get measured. But it's really not crucial that you actually measure them. But what matters is that you have these extra qubits that then get thrown away. And the reason for that is, of course, that if you start, if the system is entangled with the environment, then its entropy goes up, right? But if we're going to do error correction, we need that entropy to go back down, okay? So to decrease the entropy again, we need to throw away the entropy that we previously had. What is that entropy? It's the entropy of ancillas that are entangled with the environment. Okay. So when we end up with this state that's just I tilde tensor stuff, that stuff has a lot of entanglement between the sort of initial noise. The psi mu is describing the initial noise, and the nu is the thrown away ancillas. Okay, so you get rid of all the entropy into these thrown away ancillas. They absorb it up. Okay. Any questions about that? Okay, so we're now going to move on to a topic that, at least to my mind, is a bit simpler, a bit less technical, but super beautiful story and very, very, very important in like basically all the quantum error correction codes that you'll probably ever learn fit into this framework. Just this very general framework of things called stabilizer codes. Okay, so these are just a very general way to construct useful quantum codes. Okay. And so these stabilizer codes are going to be sort of built out of things using Pauli matrices. And so to start playing around with them, it's helpful to first define what's called the Pauli group. Okay, so the Pauli group for one qubit is just equal to the set of 8 matrices that are plus or minus the identity, plus or minus x, plus or minus z, and finally plus or minus x times z, which is of course minus I times y. Okay, so it's slightly confusing. Y is not actually a Pauli group matrix in the Pauli group. Instead, IY or minus IY is. Okay, and the reason we define it this way is that this, of course, forms a group, a non-abelian group. Write that. A non-abelian with the capital on the A rather than the capital on the N, because non is, of course, not a name, but able is. A non-abelian group under matrix multiplication. So when we multiply any two things in this group, you get something else in this group. And of course, yeah, it's a group G containing 8 elements, order 8 group. Okay. So for n qubits, so let's call 1 qubit, we have the group we'll call G. N qubits, we define Gn, go with subscript n, to just be the set of matrices plus or minus products of Pauli matrices, products of Pauli matrices with a factor of I anytime there's a Y matrix. Okay. Let's actually make that. Let's IY. Okay, so the size of this group is, well, we need to choose one of these 4 things, I, X, Z, and IY, for each of the n qubits. So that gives us a 2 to the 2n. And finally, we have plus or minus. So that gives us 2 to the 2n plus 1. Okay. Any questions about how that's defined? Okay. So let's just take a brief moment to think about a couple of properties of this group, which are going to be useful. The first is that for M and N in the group, we always have either M and N commute or M and N anti-commute. Right, either Mn equals Nm or Mn equals minus Nm. And the reason for this, it should be fairly obvious, is just that the Paulis anti-commute with each other, and the identity commutes with all of them. And when you have products, then the products either will just each of the n qubits, either the Pauli for M and the Pauli for N anti-commute, or one of them's the identity and they commute. And so you just have to calculate the overall sign you get when you move N plus N past M. You just have to count the number of the N qubits where both of them are different Pauli matrices. Okay, so the same Pauli matrix, they commute. If one of them's the identity, they commute. That clear? Anyone unhappy with why that property is true? Okay, great. So the second property is going to be that for any M in this group, we have either M squared equals the identity. I'm being a bit consistent in my notation here. Use the identity like this. Or M squared is equal to minus the identity. So for example, we have X squared is the identity, Z squared is the identity, but I times Y squared is equal to minus the identity. So this is true basically if M has an odd number of IYs in it. Okay. M squared is the identity. Then M has an even number of IYs in it. That means it's proportional to a product of Paulys, and a product of Paulys is of course Hermitian. Okay, if it has an odd number of IYs in it, then it's I times the product of Paulys, and that means it's anti-Hermitian. Okay. Any questions? Cool. Okay. So now to start creating our stabilizer codes, all we're going to do is going to choose some set of independent. So each one isn't just a product of some of the others. Hermitian. Okay, so things to the square to the identity. And commuting elements mi. Okay. So for example, we could choose on 2 qubits, we could choose x times x and z times z as our two things. So they commute, and they're both Hermitian and so on. Okay, we could also add like IY tensor IY, i.e. minus y tensor y, but we couldn't have just IY in there, both because it was anti-commute with things and it's not Hermitian. Okay.
Sorry, could you say again why having an odd number of IYs leads to -1? I would think that having any number of I's would lead to a IYs would lead to a -1.
No, because well, each I squares to give a minus sign. But if you have an even number of I's, then you have a even number of minus signs, and that ends up giving you +1.
Oh, yeah. Okay, thanks. Sorry.
Cool. No, good question. Okay, so this set of MIs generate an abelian subgroup of GN. Which we call the stabilizer group S. Okay. So it's abelian just because the MIs all commute, and so products of them will also all commute. It's a subgroup because, by definition, we're including all products of MIs in it. And yeah, they're all in G little n because G little n is a group, so any products in the group. Okay. So now we're going to define our code subspace. We say that a state psi tilde is in H code if and only if mi psi tilde is equal to psi tilde for all I. Okay, or equivalently, because they all commute, and S is just generates products of it. M psi tilde equals psi tilde for all operators M in the stabilizer group S. Okay, so the MIs all square to the identity. That means their eigenvalues are all plus or minus 1. And we're requiring for a state to be in the code subspace has to be an eigenvalue with eigenvalue plus 1 rather than eigenvalue with eigenvalue minus 1. Okay. It is a fact that each of these MIs has half its eigenvalues plus 1 and half are minus 1. Okay, so to prove this, very simple. There exists some M in Gn such that M anti-commutes with Mi. Then we have that Mi M psi tilde equals minus M Mi psi tilde. So if psi tilde Mi psi tilde equals psi tilde, Mi M psi tilde equals minus M psi tilde, and vice versa. Okay, so for each plus 1 eigenvalue, we have a corresponding minus 1 eigenvalue. Okay. So now let's think about the size of the code subspace. Okay. So basically the way it's going to work is that each additional constraint that we need Mi psi tilde equals psi tilde is going to cut the dimension of H code in half. Okay, so first we impose the first constraint, half the eigenvalues are plus 1, half are minus 1. Then yeah, so that, you know, imposing the constraint that it'd be a positive plus 1 eigenstate means that we cut the dimension of the code space in half. And then you can check, I'm not going to bother proving it, but it's pretty easy to do, that each further constraint just keeps cutting it in half, okay, as long as they're all independent. Okay, so if we have n minus k generators, Mi, then the size of H code is 2 to the n divided in half, 2 to the n minus k times, which is of course just 2 to the k. Okay, so our code subspace consists of k logical qubits. Moreover, by construction, we automatically know what those sort of right operators are to measure to know whether an error has happened and what errors happened. We're just going to use these operators Mi. Right, so the operators Mi will be the syndrome measurement operators that detect errors. So for example, if we do a measurement of all the MIs and we get +1 for all of them, then no errors happen, right? Because we're still in the code space. Okay, so we're starting to get a sense of how this is going to give us a quantum error correcting code, but we still got some way to go. We've got to work out like, actually what errors can be corrected in any given case. Suppose we have some Pauli error EA. Okay, then either EA is going to commute with MI, in which case MI EA psi tilde is going to equal to EA MI psi tilde equals EA psi tilde, or it's going to anti-commute with EA. Right, so then EA psi tilde is a +1 eigenvalue of MI. Or it's going to anti-commute. If it anti-commutes, we have MI EA psi tilde is equal to minus EA psi tilde. It's a -1 eigenvalue. Okay. For quantum error correction to be possible, we need, as we spent the first half of this lecture discussing, that J tilde, EA dagger, EB, I tilde should be equal to CAB delta IJ. Okay. Let's try to see how that will happen, what will happen for these stabilizer codes. There's really three possibilities. The first is that EA dagger EB happens to be a stabilizer. It's contained in this group S generated by the MIs. Okay. In that case, we have J tilde, EA dagger, EB, I tilde. Just EA dagger EB is contained in S, so it's a +1 eigenvalue of I tilde. So we have that it's J tilde, I tilde, which is of course this delta IJ. Okay, so is that consistent with the condition we need above? Yes, it is, right? It works because this inner product doesn't depend. It's just delta IJ with no I dependence, right? So that's great. So if we have things like that showing up, can do error correction just fine. So the second possibility, so that really corresponds to EA and EB act the same way on the code subspace. So we had that in the short code, for example, right? Some possible errors, like it didn't matter whether a Z got applied to the first qubit or to the second qubit, it did exactly the same thing to all states in the code space. And that's fine because then you can correct either one, even if you don't know which is which. The second possibility So there exists some mi such that EA dagger EB anti-commutes with mi. Okay. Then we have J tilde EA dagger AB I tilde. Well, EA dagger EB I tilde is going to be a -1 of eigenvalue -1 for mi. J tilde has +1 eigenvalue because it's in the code subspace. So this is going to be equal to 0. Okay. Again, it's proportional to something times delta ij. So that's fine. So this is again consistent with quantum error correction. The third possibility is that for all the mi, we have EA dagger EB commutes with mi. However, EA dagger EB is not contained in the stabilizer group. This is also a possibility, and in general, this will always exist. So what happens in this case is that EA dagger EB acting on psi tilde is contained in the code subspace because it still has the same eigenvalues as same eigenvalues for the mi's as psi tilde did. They're all still +1, so they're commuted with everything, but is not in general equal to I tilde. Okay, because if it was, then yeah, it would be contained within the stabilizer group S. Okay, so this sort of acts non-trivially on the code subspace. Sort of J tilde EA dagger EB I tilde is not in general proportional to delta ij. So these errors, if we have error A and error B both being yeah, either EA has to be uncorrectable or BB uncorrectable. We can't correct both at once. Okay. Because we can't distinguish between some state with error B applied and a different state with error A applied. Okay. So we need, yeah, go ahead.
Yeah, I just had a quick question on case 2.
Yep.
So we make the argument that because EA dagger EB anti-commutes with MI, then the EA dagger EB I tilde, that has to have negative eigenvalue for MI.
Yep.
And then we assume that the state J has plus eigenvalue for MI because J is part of the
J's in the code subspace. Exactly.
Code subspace. And do we know that MI doesn't connect +1 and -1 eigenvalue states?
What do you mean MI doesn't connect? So like, so MI is some Hermitian matrix, so it has a orthogonal set of +1 eigenvalue eigenstates and orthogonal set of -1 eigenvalue states, and they're all orthogonal to one another.
I see.
Right.
Okay, so there's no possibility for it being like non-diagonal in the.
No, it's because it's Hermitian.
Okay.
Yeah. It's Hermitian, so it has an orthonormal set of eigenstates. It's different eigenspaces for different eigenvalues are orthogonal to one another.
Oh,
good question. Okay. So what we need is that case 3 to never happen for allowed errors. So for example, suppose we find S such that the commutator of EA dagger EB with S being 0, but EA dagger EB not itself being in S. So suppose that whenever that happens, then it implies EA dagger EB acts non-trivially on at least D qubits for some D. Okay, so just say we found some S that's such that that's true. Then, if our set of allowed errors consists of Pauli's acting on at most a half D minus 1 qubits, then EA dagger EB, each of them acts on at most a half D minus 1 qubits. So EA dagger EB acts on at most D minus 1 qubits. Case 3 never happens. Quantum error correction is possible. Okay, we found a quantum error correcting code. Make sense? Any questions about the general framework of how stabilizer codes work? Otherwise, I'm just going to spend the last 10 minutes or so just talking about some simple examples of stabilizer codes. Okay. So can anyone think of an example of a stabilizer quantum error correcting code? What's the one quantum error correcting code very explicit quantum error correcting code we've seen so far?
Shor's code.
Indeed. And it turns out Shor's code, along with many, many other things, is an example of a stabilizer code. Ooh. Okay. So how did Shor's code work? Well, we had 9 physical qubits. We had 1 logical qubit that we were trying to encode. So for a stabilizer code, we would need n minus k 8 stabilizer mi. Okay. And for the Shor's code, what are these things? Well, they're just the things we use for our syndrome measurements, right? So to correct the bit flips on the first 3 qubits, we measured Z12 and we measured Z23. For the second 3 qubits, we measured Z4, Z5, Z5, Z6. And for the last 3 qubits, we measured Z7, Z8, and Z8, Z9. And then to correct the phase flips, we used X1, X2, X3, X4, X5, X6, or one big product, and X4, X5, X6, X7, X8, X9. Okay, so we have 6 Z stabilizers, 2 X stabilizers. These are our 8 stabilizers. And indeed, the code subspace is just the simultaneous +1 eigenstates of all these operators. Right, if we got +1 in all our syndrome measurements, that meant that no error had happened. We didn't need to do anything. Okay, so that is the code subspace edge code. What we found is that Shor's code can correct any 1 qubit error in the stabilizer language. It's the equivalent. This comes from the fact that EA, dagger, EB commuting with everything in the stabilizer group, but not being in the stabilizer group implies that EA, dagger, EB acts on at least 3 qubits. Okay, so the D, as we call it above, sometimes called the distance of the code, is equal to 3. Okay, there's a notation which is commonly used to characterize quantum error correcting codes, which is useful to have seen, which is you use these double square brackets, and then you write the number of physical qubits, the number of logical qubits, and the distance D, which is like 2 times the number of qubits that you can correct arbitrary errors on plus 1. So Shor's code, this notation really comes from classical error correcting code. But Shor's code has 9 physical qubits, 1 logical qubit, and distance 3. Okay. Any questions about that? Okay. But the great thing about the stabilizer code framework is that we aren't so limited compared to Shor's code with the sort of codes that we can come up with. And we can actually come up with significantly better codes than Shor's code. So pretty soon after Shor's code was invented, something called the Steam code was invented. Which hopefully will be talked about more in the discussion on Monday. I think that's the current plan. So this code is still based on classical error correcting codes, but it's slightly more sophisticated classical codes than just the repetition code. It's based on something called Hamming codes. Okay, and so this code, slightly better than the Shor code, encodes 1 logical qubit in 7 physical qubits, and it still protects against arbitrary errors on 1 qubit, so it has a distance D equals 3. Okay, and it's again an example of a stabilizer code. And the stabilizers are just the following products of Paulys. Don't worry too much about the details. I'm just writing them here for completeness. But basically you have, you check products of Zs on 3 different sets of 4 qubits. And then you also check products of X's on the same sets of 4 qubits. So those are your 6 stabilizers, okay, because we have 7 physical qubits, 1 logical qubit, so n minus k is equal to 6, and they just are what they are. Okay, so the final code can do even better. So that's sort of as far as people got based on like things they already knew from classical error correction. But actually you can come up with a 5-qubit code. It's very boringly just called the 5-qubit code. And yeah, this has no sort of classical analog at all. It's just fundamentally a quantum error correcting thing that you need this framework of stabilizer codes to come up with. And so this is, again, 5 physical qubits now, 1 logical qubit, and distance 3. Okay, and stabilizers. We have 4 stabilizers. They're X1, Z2, Z3, X4, X2, Z3, Z4, X5, X1, X3, Z4, Z5, and Z1, X2, X4, Z5. Right, so unlike the Steam code, which sort of has a logical structure of where you're measuring the same products for Zs and the same for Xs, similarly the Shor's code, it's like something you might come up with by hand. Pretty much this is just, you have to search for like arbitrary sets of generators for your stabilizer groups that just have this nice property of having D equals 3. Okay. So, there's not a lot of insight you can get out of the 5-qubit code. There's certain ways of thinking about it that's slightly better than what I said, but I'm not going to go into them. Just is a code, a nice stabilizer code that exists. You might wonder, can we do even better? If we can get down to encoding 1 qubit in 4 qubits, can we get down to 5 qubits? Can we get down to say 1 in 4 or even 1 in 3? Right, like for classical things, then you can do 1 in 3 with the repetition code, and the answer is no. This is the best you can do for encoding 1 qubit, and the proof of this is quite simple. Suppose we only want to recover errors on some subset, some fixed subset of qubits. Okay, so rather than correcting errors on a certain number of arbitrary qubits, we correct any errors on some fixed number of qubits. Okay, then E dagger A and EB both act fixed errors. It's called, fixed subset of L qubits. Both of these act on the same L qubits. So this means EA dagger EB itself acts on at most L qubits. Error correction is therefore possible so long as L is strictly less than D. Okay, so to correct errors on arbitrary qubits when we didn't know which ones had experienced the error, we could only correct like errors on a half D minus 1 qubits. But now we can correct errors on D minus 1 qubits. Suppose we had a 413 code, right? So it can protect arbitrary errors on 1 qubit, arbitrary errors on 1 qubit, i.e. D equals 3, but it's encoded in only 4 physical qubits. then what we can do, give 2 of the physical qubits to Alice and 2 of them to Bob. From the point of view of each of them, they have errors on a fixed set of 2 qubits. Right, because they each lost 2 qubits that got sent to the other person, but they know which qubits they were that they lost, and so they can recover errors on them. But of course, if Alice and Bob both recover the state, then we've successfully cloned a quantum state. And you proved in the homework a long, long time ago that that's definitely impossible. Okay. So this is obviously impossible. Okay, so that's all I have to say for today. On Tuesday, we're gonna have our last lecture on sort of quantum error correction stuff. Going to briefly talk about the most beautiful quantum error correction code of all, which is the toric code. Actually, again, an example of a stabilizer code. Just going to sort of briefly introduce it, not go in much detail. Then I'm going to, again, just give a sort of high-level overview of, okay, sure, you can do quantum error correction, but when we're wanting to actually do computing on these, like, logical states, then that gets a lot harder, right? Because you've got to be like doing stuff and still keeping everything error corrected and not having like the errors blow up as you try to do the error correction step and like have errors as you do error correction and so on. And so that's called fault tolerant quantum computing. It's a beautiful theorem that says as long as your sort of errors on your like original physical qubits are small enough, then you can do fault tolerant quantum computing, and you can make the probability of logical errors in your computation arbitrarily small. Okay, so yeah, that is next time. But anyone have any questions on the last stuff there?
I did have a quick question. It wasn't necessarily on this stuff. That was a little while back. If that's okay. When you were doing the proof that the MIs had either +1 or -1 eigenvalues, we started by assuming that there existed, I think, one that anti-commuted with everything else. How are you guaranteed that such a
the MIs? The MIs are just products of Pauli's on each qubit, right? So just pick. They're not equal to the identity, so they must have a non-trivial Pauli, like an X, Z, or an IY on one of the qubits. Right, and then you choose one of those qubits where it has that, and then choose a different Pauli acting only on that qubit that's the identity everywhere else. Okay, so then that will anti-commute with MI. Okay, because the identities all commute through, and the Pauli anti-commutes.
I see, but then if we were to choose the same Pauli, then it would commute.
Same Pauli would commute, but we can always choose a different Pauli.
Okay.
Cool.
Okay, thanks.
Any other questions?
I'm having trouble understanding what d, the distance, means.
Yeah, it's sort of stupid that it's. Look, what it means is it's the how complicated the Pauli needs to be to do something non-trivial to the code subspace, i.e. not just act as the identity on the code subspace, but also take states in the code subspace to still be in the code subspace, right? So you Pauli's can do 3 things. Let's M acting on psi tilde equals either just psi tilde. Okay, in that case, it's not done anything at all. 2, some state sort of phi that is orthogonal, some state phi that's orthogonal to the code subspace, i.e. has eigenvalue -1 for one of the MIs, or 3, some phi tilde that is in the code subspace, but that's not equal to psi tilde necessarily, right? So this third case is that the Pauli M acts as a non-trivial logical operator on the code subspace. Okay. So this D is the minimum number of qubits that M, this number of qubits M has to act on for case 3 to be true. Okay, how does that relate to the sort of number of qubits that we can error correct? Well, certainly if your error like does M, then you're in trouble, right? Because your error has changed the state, but it's still in the code subspace, so you can't detect that an error has happened at all, right? So clearly you can't correct M, but you also have to worry, what about if you have two errors, EA and EB, such that EA, EB dagger equals M, right? Well, in that case, if you don't know whether error A happened or error B happened, then EA happening on one state, psi tilde, is equal to EB happening on another code state, psi tilde, right? So you can't tell, if you just measure that the state is this thing, then you can't tell whether it was originally psi tilde and error A happened, or it was originally phi tilde and error B happened. Okay, so that's how you get that you can only correct errors when on strictly less than a half D qubits. That makes sense?
So in Shor's code, why is it like 3? Why is D equal to 3?
Yeah, so it just is true, right? Shor's code can correct any errors on like 1 qubit, right? Which means that if I have some error EA that acts on 1 qubit and some error EB that acts on another qubit, then this is never true for 1 qubit EA and EB. Okay, and that means for 2 qubit things, EB dagger EA, then case 3 never happens. Okay, so the minimum number of qubits where case 3 can happen, where it can do something non-trivial in the code subspace, is D equals 3.
Okay.
It's really stupid the notation uses D. The notation, it should just be like the notation is like 511 or 911, where 1 is the number of qubits that you can correct errors on, because it's like basically equivalent information. It's just for some reason based on traditional notation for classical channels, then yeah, people use D instead. Okay.
So this means like Shor's code can't correct errors for like Bell states. Is that what this means?
Well, how you can't encode a Bell state in Shor's code, right? Shor's code just encodes 1 qubit. It's about the types of errors that can be corrected, not the types of states that can be corrected. It's if two of the 9 qubits get corrupted, right? If I apply a bit flip to 2 different qubits, then Shor's code can't detect that that's happened. Shor's code will think that just 1 bit flip has happened on a 3rd qubit. And then when it undoes that 1 bit flip it thinks happened, then it will get the wrong state. So the state will have got corrupted. It's like with the classical repetition code, right? If I started with 111 and then 2 of them got flipped, right? Then I'm going to look at that state and I'm going to go, oh, that middle bit got flipped. And so it should go to 0, 0, 0. But now the state has changed. I've ended up concluding this is the wrong thing.
Okay, yeah, I get what it means then. Thank you.
Okay, cool.
Yeah.
Awesome. Any other questions?
Yeah. Do you have office hours today?
Yes.
All right, cool.
Yes.
So we
Yeah,
can come in and
ask
talk
that.
about the
Yep.
project and.
Yep, absolutely.
All right, great. Thank you.
Okay.